Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Interview questions and answers in Absorption and Gas Processing, Part 1. I would appreciate if you subscribe to the channel. We are striving hard to deliver valuable knowledge content for your career progress. So subscribe now before you forget. For every question, you are given 20 seconds to think about your answer. Then the answer will appear. Check your answer is correct. Absorption and gas processing. Gas processing by absorption is an important mass transfer process in oil gas industry, refineries, petrochemical and fertilizer industries. Processing of raw LPG from the crude distillation unit and cracker to remove impurities such as hydrogen sulfide and carbon dioxide is a secondary processing step in refineries. Likewise, removal of contaminant gases from waste gases and byproduct gases by absorption in petrochemical industries is also a secondary processing step. Hence, it is important that you are aware of these operations. Subject matter expert can ask any questions in refinery operation. Question number 1. What is the difference between physical absorption and chemical absorption? Give 2 examples for each process. What is a notable feature of the chemical absorption process? Your time starts now. Your time is up. The answer. Physical absorption involves straight dissolution of absorbate, which is the contaminant gas, into an absorbent, which is a liquid or a solvent. The gaseous contaminant being absorbed must be at slightly soluble in the scrubbing liquid, that is absorbent. Mass transfer to the liquid continues until the liquid approaches saturation. At saturation, equilibrium is established between the 2 phases. In other words, the mass transfer rate of the contaminant into the liquid is equal to the mass transfer rate of the dissolved species back into the gas phase. Accordingly, the solubility of the contaminant in the liquid creates a limit to the amount of pollutant removal that can occur with a given quantity of liquid. Chemical absorption is a dissolution of solute accompanied by irreversible chemical reaction. The notable characteristics of the chemical absorption is that the reaction provides a means to overcome the solubility limit by providing reactants in the liquid phase that react with the dissolved gas contaminant, forming a dissolved compound that cannot exit the liquid. When the gas chemically reacts with the liquid or some component in the liquid, the concentration in the liquid phase is low or zero. This enhances mass transfer through the liquid film. Hence, absorption followed by chemical reaction in the liquid phase is often used to get more complete removal of a solute from a gas mixture. If the reaction is irreversible, which is normally the case at absorption conditions, then the equilibrium partial pressure is zero. In general, absorption with chemical reaction is enhanced due to the reaction. The enhancement is expressed in terms of an enhancement factor E. E is defined as a rate of take-up of A from gas with chemical reaction occurring to the rate of take-up of A with direct or physical absorption. Chemical reactions can increase rate of absorption, the absorption capacity of the solvent, selectivity to preferentially dissolve only certain components of the gas, convert a hazardous chemical into a safe compound. For mass transfer in simple physical absorption, the absorption rate expression should account for the gas component, the equilibrium relationship, gas and liquid phase transfer resistances. For mass transfer with chemical reactions, the absorption rate expression must account for both the gas component and liquid reactant, the chemical reaction rate, the equilibrium relationship, gas and liquid phase transfer resistances. Examples of physical absorption type are 1. Absorption of acetone in water. 2. Absorption of hydrogen chloride in water. Examples of chemical absorption type are 1. Absorption of carbon dioxide in sodium hydroxide. 2. Absorption of carbon dioxide and hydrogen sulfide from refinery and natural gas in amines, which is irreversible chemical absorption. Question number 2. Draw a equilibrium solubility curve for absorption of gaseous component in liquid considering the solution is dilute. It's modest liquid concentration range. Name the law that is applicable for this case. Your time starts now. Your time is up. The answer. For dilute solutions, the Henry law is applicable. Henry's law states that for dilute solution, P star equal to H into X, which H is the Henry law constant. The units of H in this equation is atmosphere per mole fraction. Dividing both sides of the equation by total system pressure P, you get P star by P is equal to H by P into X. The above equation can be rewritten as Y is equal to H dash X. The units of H dash is mole fraction in vapor per mole fraction in liquid. Where Y star is a mole fraction of solute in the gas phase at equilibrium, which is P star by total pressure P. H or H dash is Kennedy's law constant. X is equal to mole fraction of contaminant dissolved in the liquid phase at equilibrium. Note, H is dependent on the total pressure. P star is a partial pressure of gas in equilibrium with the liquid. For a gaseous mixture, for absorption of component A, we can write Ya is equal to H dash to Xa. Illustrated in this figure is an equilibrium solubility line for sulfur dioxide in water. A plot of X versus Y. Note that the equilibrium line starts from 0. Question number 3. What happens to the equilibrium solubility if there is a change in temperature and pressure? Your time starts now. Your time is up. The answer. Absorption is influenced by the system pressure and operating temperature. Absorption is favored by high operating pressure and low operating temperature. Henry's law states that the solubility of a gas in a liquid is directly proportional to the operating pressure of the gas, that is, the pressure above the surface of the solution. If the pressure is increased, the more gas molecules dissolve into the solution. As the temperature increases, the solubility of gas decreases. Equilibrium solubility graphs at various temperatures give you understanding of the effect of temperature on gas absorption. This plot is an illustration of equilibrium solubility of a gas at different temperatures. Note that for a gas concentration of 0.2 mole percent, the equilibrium concentration of the liquid is greater at 10 degrees centigrade than at 30 degrees centigrade. Question number 4. If you are asked to design an absorption column for absorption of gaseous mixture in a solvent, what are the process data needed as specifications to start the design process? Explain with a sketch. How will you determine the liquid rate required? What will be the design output data you need to construct the column? Your time starts now. Your time is up. The answer. The parameters that should be specified to start the design process include gas feed rate, concentration of gas inlet and outlet of the column, a liquid inlet concentration, equilibrium data to construct the equilibrium curve. Shown in this figure is a sketch of an absorption column with the design data. The data circled in the figure ought to be specified to start the design process. The liquid exit concentration and the liquid rate ought to be determined. By plotting this data on an equilibrium diagram, the minimum liquid flow rate required to achieve the specified solute concentration in the exit gas Y1 can be determined. The minimum liquid flow rate is that at which the outlet concentration of the liquid flowing out of the column is the maximum in value. The maximum concentration X max is the concentration of the liquid which is in equilibrium with the inlet solute concentration of the gas mixture flowing into the column Yn plus 1. This figure illustrates how the liquid flow rate is determined from the equilibrium solubility plot and the specification data provided for the design of the absorption column. From the gas inlet concentration, draw a straight line such that it cuts the equilibrium curve at point O. And this point on the equilibrium curve represents the maximum liquid concentration point. The liquid concentration equilibrium with the inlet gas concentration. Since the liquid concentration of solute at the column inlet is 0, the gas outlet concentration Y1 on the y-axis indicates the operating point. Connect this point Y1 and the point O on the equilibrium curve. The line obtained is the minimum operating line. The slope of the minimum operating line is L by V minimum. At minimum operating line, you need infinite number of stages to achieve the given degree of separation due to pinching. There is no driving force at point O. So the actual line is decided by selecting a point P on the line connecting the outlet concentration Yn plus 1 and the point O. The line connecting the gas outlet concentration point Y1 and the point P is the actual operating line. The slope of the minimum operating line is obtained from Yn plus 1 minus Y1 equals L by B minimum into X max minus XO. The minimum liquid flow rate can be determined from the above equation. The design liquid rate for absorption column is 1 to 1.5 times the minimum liquid rate. The actual operating line should lie above the minimum operating line and the equilibrium curve so that there is enough driving force. In summary, the design will lead to the determination of a liquid or solvent rate, a liquid exit concentration, number of stages required to achieve the degree of separation specified, choice of tower, internal, whether it is tray or packing, the column diameter, column height, and column pressure drop. Question number 5. A process plant generates waste gas containing 0.4 mole percent SO2. As per the environmental regulation, SO2 has to be removed before the gas is discharged to the atmosphere. The company intends to treat the gas by scrubbing with water to reduce the concentration to 0.07 mole percent. It has two options to use water. One at 20 degrees centigrade, two at 30 degrees centigrade. Which option will result in smaller size absorption tower? Take L by G the same for both cases. Your time starts now. Your time is up. The answer. Illustrated in this figure is the construction of Mercaptan diagram and determination of number of theoretical stages for absorption operation, 1 with water at 20 degrees centigrade, 2 with water at 30 degrees centigrade. The equilibrium diagrams for the two temperatures are shown in this figure. Select the operating point in such a way that it cuts the gas inlet concentration line at P, which is the operating point at the tower bottom. Now construct the Mercaptan diagram and determine the number of stages, first at 20 degrees centigrade, then at 30 degrees centigrade. The number of theoretical stages at 20 degrees centigrade is approximately 2.5, and the number of theoretical stages at 30 degrees centigrade is approximately 3.8. The number of stages required for operation at 20 degrees centigrade is less compared to the operation at 30 degrees centigrade. Lower equilibrium solubility will lead to lower absorption and will increase the number of equilibrium stages to get the desired degree of separation. Therefore, the column height will be less for absorption at 20 degrees centigrade. For a sieve tray, the height of the tower H is equal to number of theoretical stages into tray spacing. Thus, the height of the tower will be smaller for operation at 20 degrees centigrade. Hence, the cost of the tower will be lower. Increase of number of stages will also result in greater pressure drop and higher energy cost. But to achieve 20 degrees centigrade, you have to cool the water in a chiller, which will increase the refrigeration cost. The operating cost will be higher. So you have to estimate the total cost of operating the absorption column at 20 degrees centigrade and at 30 degrees centigrade. The option that has the lowest total cost should be selected. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you have finished viewing the video. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.